of t, right? An explicit function of t. So any questions before I go on here? Now, something you guys are going to ask me as soon as you realize the question is, can't I just plug in the formulas and just differentiate? Wouldn't that just be the same? You know, like, isn't f composed with r of t? Well, that's just equal to, you know, f of what? 2 cos t and 3 plus t squared, right? So if we feed our f a diet of 2 cosine t and 3 plus t squared, well, then the formula is straight up, you know, 2 cosine t quantity squared plus, you know, parentheses 3 plus t squared squared. And as such, the derivative with respect to time of f composed with r of t is just equal to what? We get what, 2 times 2 cos t times what? Yeah, negative 2 sine t. And over here we get 2 times 3 plus t squared times 2t. Also known as minus 8 cos t sine t plus 4t times 3 plus t squared. Oh my goodness, what do you know? It's the same. So some students realize this, and then they come to this false belief that they don't need the chain rule, that they can ignore it. It doesn't matter. Why are those students wrong? The students are wrong because you could run up against an example like example 6. Given fx of 1, 2 is equal to 13, and fy of 1, 2 is equal to 10, if r of t is equal to, 1 plus t squared, comma, 2 plus t cubed, find the derivative at time 0 of f of r of t. See, the problem now is we have no formula that tells you how the intermediate variables work for x and y for this function, right? The function f is not given. Only partial information is given about f. But the thing is, we can do, ddt at t equals to 0 of f of x of t, y of t, all right? By the chain rule, this is equal to partial f, partial x at x of 0, y of 0 times dx dt at time 0 plus partial f partial y at the point x of 0, y of 0 times dy dx, dy dt at time 0. So, this is x, right? For the path. This is y for the path. So, the answer is rather unsatisfying. Permission to change things slightly. We will take this 2 and devote it to destruction. There we go. Pox on your house. You're gone now. Yeah. So now dx dt is 1 and dy dt is 3t squared, right? So going down here, I've given you fx of 1, 2. By the way, x of 0, y of 0 is what? X of 0, y of 0. In other words, r of 0 is 1, 2. That was by construction here, okay? So I know that this is fx at 1, 2 times 1 plus fy of 1, 2 times, well, 3 times 0 squared. In other words, the answer is 13. But here I can't calculate the gradient of f. I don't have the formula. I have to use the chain rule. You see, it's unavoidable. Yeah? Okay, so this is the chain rule for a function of 2 variables evaluated at a path in 2 dimensions. What do you think the chain rule looks like for a function of 3 variables evaluated at a path in 3 dimensions? Let me write it out, and then I'll tell you another notation for it. So if we're talking about the derivative with respect to time of f of x of t, y of t, z of t, right? Then the way this works is partial f, partial x times dx dt, plus partial f, partial y times dy dt, plus partial f, partial z times dz dt. This is the gradient of the level function f dot product with dr dt, right? If I'm using r of t equals to, as usual, x of t, y of t, z of t here, yeah? So here you go. This is the chain rule for a function of 3 variables evaluated at a space curve, at a path, rather. And once more, to be clear, more notation here. This ddt of f composed with r at the time t, it's equal to the gradient of f at r of t dotted with the r dt of t. Like there's the, of course, the partial derivatives of f here have to be evaluated at the path to be clear. All right? So I've been advertising that certain things I can't prove until I have the gradient, the chain rule, right? Let me show you why I said that. We'll start with the level curve. Level curve. F of x comma y equals to a constant. If we have a parameterization of that level curve, what's that look like? That's r of t is x of t, y of t, right? How is it related to this equation, though? It's related in the following way, right? F of r of t has to be equals to a constant if, t maps to r of t parameterizes the level curve. Right? This is what we mean by parameterizes level curve. You plug the formulas into the level equation and it works, right? Could be f of x is x squared plus y squared. If we put x equals to cosine t, we put y equals to sine t. It works. X sine squared plus cosine squared is 1, right? Parameterization. Differentiate this now. What do we get? Differentiate this. If we look at this, the derivative of this is the gradient of f evaluated at r of t, right? Dotted with dr dt, right, at the point t, is equal to the derivative with respect to time of a constant. What's the derivative of a constant? 0. What does this say about the relation of the geometry? Look, it's right here. So here's the point. This is the tangent direction, dr dt at, let's say, time t naught, right? And this equation right here says that the gradient is perpendicular. the gradient is perpendicular. I didn't have calculus before this, but I could only argue in terms of examples and common sense about what it meant. Now we have a proof that the gradient vector is perpendicular to the tangent direction to the curve. If you don't want to change levels, follow the curve. That's a level curve, right? Level surface, f of x, y, z equals to a constant. If we have a path that lies on that curve, then we have f of r of t equals to a constant, right? So here I'm talking about some surface, right? This is the set of all points f of x comma y comma z equal to a constant. And I'm saying, suppose you've got a path that's on this thing, whatever, but it's lying in that surface. What equation does the typical point here, r of t, have to satisfy? It must be that when you plug it into the defining equation, you get the constant, right? So like, for example, we could have x squared plus y squared plus z squared equals to 1 is my equation, and my path might be, cos t 0 sine t, right? There you go. That's a particular path on the sphere. I think it's like the great circle, like this, right? Anyway, there's an example. Differentiate this. What does it give you? The gradient of f at r of t dotted with dr dt has to be equal to the derivative of the constant, which is 0. So this shows you that the gradient to the level function for the surface has to be perpendicular to what? It's perpendicular to the tangent vector of the curve, right? So if I tried to draw a picture of this, here's a point, right? How many different curves go through that point on a surface? The answer is yes, right? I mean, like, there's a lot of them, yes? But no matter which one you look at, the tangent vectors to those paths, they are all perpendicular to that one defining normal vector, gradient of f, at that point. So this thing, gradient of f, at the point r of t naught, let's say this point right here is r of t naught. If you like, we call it point P. So we're talking about the gradient of f at P. Well, the gradient of f at P defines the normal direction to what we'd like to call the tangent plane to the surface. Oh, see, there's a new idea here, because a surface doesn't have to have the same tangent plane at different points, right? As you move along the surface, the gradient vector points different directions, different places, and you got different tangent planes, different places. But locally, the tangent plane is like the best approximation to the surface. Anyway, so I just wanted to show you the chain rule and show you two of its chief geometric applications today. We'll do many more chain rules tomorrow. I think I owe you guys like a surprise attack mission tomorrow. There will be one in class, start a class. It shouldn't take too long.